Okay, I don't hear complaints, so that's a yes. All right, so in the next 30 minutes, we're gonna change a little bit gears, and we're gonna go into the world of TOO's capabilities, so this is it all good? Okay, I heard some noises, but I'm assuming everything is fine. All right, so okay, all good. All right, I take it as a yes. So
yes, Raffaella, thank you. It's all good.
All right, awesome. So I'm gonna just give you a little bit of an idea of the path that started in 2015 when there were 4 people that were part of the multi-wavelength and GW counterparts subgroups. And right now, I did a census in the past few days. We are 235 people that expressed interest, and most of these people have already contributed to sometimes substantially to the documents that led to what I believe is now reality, these targeted opportunities on LSST. So let's get started. Just a very brief scientific motivation of why TOOs are really so needed on LSST, what type of science we can realize that could not be done otherwise. And of course, we all know we live in this world of multi-messenger astronomy with gravitational waves. And the beauty of the game where we are in right now is that we have gravitational waves that give us all the information about what happens before the merger. And then we have light, if we can capture it, that can tell us everything about what is happening after the merger. So if we can put the 2 messengers together, this gives us the opportunity to actually understand the before condition and the after condition, opening up a lot of physics that was not accessible before. So what can we really do with this type of investigations? Well, we can understand a lot about these extreme physical conditions that happens in mergers of compact objects like neutron stars and black holes. And here I just listed some physical quantities that we can constrain once basically we know where to look. So 170817 is still the first, but also the only object, celestial body with a very solid association of gravitational waves and light. And here I'm showing, to remind all of us, the light curves, the optical to near-infrared light curves of the kilonova that resulted from observations from thousands of scientists all around the world, actually. And as we all know, there are multiple components of emission, which will be very important for the strategy that LSST, that the Rubin will adopt potentially for targeted opportunities for these objects. So what do we want to do by capturing this light? Well, we want to understand how much mass is ejected by these neutron star mergers, which is also another way to understand how the universe was chemically enriched during its entire history. And so by monitoring these counterparts, we are answering to some very fundamental questions in nature, like how the heavy elements came to be. So this is just a beautiful slide to remind us that if we know where to look and we can point other spectroscopic facilities, we can actually see real evidence for this R process, so production of heavy elements in mergers. And suppose we don't care about the chemical enrichment of the universe, well, there is a lot of physics that is enabled by knowing where to point. And here I just mentioned 2 big areas. One has to do with how nuclear matter behaves under extreme conditions. So understanding the equation of state of dense nuclear matter. Why? Because that is basically the colors of the emission that we will see has this information embedded. Or suppose you don't care about neutron stars and how matter behaves under those conditions, but you're excited about cosmology. Well, there is also a possibility to make some progress in cosmology by using counterparts to gravitational waves. This is just a motivation slide, but all of this dream physics that we can constrain relies on the understanding, the capability to understand which among all of these little dots, all of these potential EM counterparts, which of these ones is the real counterpart of the gravitational wave event. And this is where clearly LSST can play a fundamentally important role. So we are at the beginning of this multi-messenger world with gravitational waves. And the question that is very natural to ask ourselves is, well, we have found light from one neutron star merger, and we were able actually to find photons all across the entire spectrum. So what is the frontier once we have seen one? Where do we go from here? And here is my answer. So first of all, we have seen n=1 neutron star merger with gravitational waves and light. Of course, the next step is we want more. We want to understand populations. So we want to understand the diversity of the outcomes of these binary neutron star mergers. And fundamentally, what we would like to know is, given these initial conditions that we understand from gravitational waves, how does the outcome look like? So what type of light do we produce, and what type of object do we produce? And one of the big questions that for 170817 we have to be very honest is not entirely settled is, what is the nature of this new compact object? Is it a new neutron star, bigger neutron star, or it is a black hole? The second point that we can address is maybe there are additional emission components, some of which might not have been present in 170817. So for 170817, one of the big mysteries is still trying to understand the properties of the blue emission component in the kilonova. And for 170817, because of observability constraints, we were not able to get on target before 12 hours after the trigger, the GW trigger. So a question that is completely open is, what happens in those 12 hours? Are there new components that we missed? And there are theoretical expectations for these new components to be actually there. So among those here, I want to emphasize this free neutron precursor that is being theorized by Brian Metzger, among others. That is a component that should shine bright, but at very, very early times that for 170817 we just missed. And then another big dream, I would say, would be to find a counterpart of a black hole neutron star merger. So we have seen these mergers in the gravitational wave from the gravitational wave perspective, so that those have been detected by LIGO and Virgo already. But we failed to find any EM counterpart. And there, the big question is there anything that has to be seen, in the sense that we know that the prediction in this case is a little bit all or nothing, in the sense that it depends where we do disrupt this neutron star with respect to the horizon of this black hole. So we would like really to understand what type of light these mergers produce, if any. Do they launch a jet, or maybe they don't? And here, I just want to emphasize this prediction for neutron star black hole mergers, where it's on the EM side is literally all over the place. It goes from no light at all to be seen to maybe something that is instead bright to be seen. Another big question mark is about counterparts of the black hole mergers. There has been some proposals in the literature, but I think the entire community would agree that there is no solid association of any electromagnetic counterpart to a black hole mergers. There has been definitely a lot of discussion with some proposals, but we still don't know what's the answer, the final answer is. And last but not least, what are the counterparts to sources of gravitational waves that are unidentified? So those sources that we can associate to black hole mergers, or any type of no merger so far. And then these are, in my opinion, the 5 big directions of the after 1708-17 era. And then if we try to translate these scientific themes into what type of capabilities do I need to realize this scientific potential, well, the solution is pretty easy. That first of all, we realize that some of the scientific cases do need deep observation. So you need a facility, and we're talking here about optical sky, and you need a facility that goes reasonably deep. And then the other thing that we need is not only you need to go deep, but you also need to get on target reasonably fast. So we need to get on target promptly. So those are the 2 big needs that we have if we want to realize the potential of this new scientific direction. And here is where LSST can play a huge game. So early in 2015, we started thinking about it, and we soon realized that if you just rely on the main survey of LSST, that would not be a good idea, in the sense that for sure there will be some of these counterparts of mergers falling inside the field of view of LSST just by chance. That is absolutely correct. However, the capabilities to go from those few detections into a value when it comes to how much mass was ejected, what was the velocity of that mass, what is the composition of that mass, that is where we fail if we rely just on luck. So, and this is our back of the envelope calculation that we put out early in 2016, just to send a message that if you want to have coverage of the entire or a significant fraction of the GW localization area, if you want to have colors, which is another way of saying if you want to really be able to constrain the physics behind the event that you're seeing, then you can't rely on just the main survey to just getting some fields just by chance. And we do need to have a new mode of observation, which are these target of opportunity capabilities, which effectively means interrupting what the instrument is doing and repointing in some other part of the sky. So I'm sure all of you are familiar with how 1708-17 the search was performed. 1708-17 was at 40 megaparsecs, which is literally around the corner for this type of science. And in that case, it made a lot of sense to go down with a galaxy-targeted search, which means that instead of just tiling the entire sky, I try to understand where the galaxies are, because I know that that is where most likely the progenitor will be. So I will increase my chances to get something by targeting some parts of the sky. That made a lot of sense for a target that is nearby, mostly because we know very well where the galaxies are, but that knowledge soon deteriorates when you go to larger distances. And for sure in the LSST era, you will get to a situation where basically, given the field of view of LSST and the distance of the average GW trigger, it will not make sense to do galaxy-targeted searches for your average trigger. And there's just another slide to remind us that the counterparts are faint. So you see there a 1708-17 like kilonova that I misplaced at different distances corresponding to the redshift. So you see on that slide, just to tell us, yep, we are dealing with counterparts that are faint. So this is another slide to quantify the same concept that I told you. So what we did here, working with an undergrad student, Chris Martinson, we created some realization of kilonovae that looked reasonably similar to 1708-17, and we played around a little bit with the mass. And then we asked ourselves, how would they look like through the LSST filters? And we placed them at 2 different distances here, 100 megaparsecs and 200 megaparsecs. And then we asked ourselves how bright these counterparts are. And just keep in mind that during O3, the median distance of neutron star mergers was around 250 megaparsecs. So 200 megaparsecs, it's not unreasonable at all as the average, your average neutron star merger. So what is the key point, take home point here is that you need to go reasonably deep to actually have some chance to detect the counterpart. And here we played around with 30 seconds exposure time, 180 seconds exposure time. What we mean is take multiple exposures and trying to go deeper, and to show that we are dealing with faint counterparts almost for sure on average. And this is to emphasize how current facilities would do. DECAM does pretty reasonably well, and you can see the ZTF limits where they would be, and then you can see instead where LSST with a very deep exposure would get us. So this motivated us to write this white paper in 2018. I want to emphasize the long list of names that you see there. All of these people contributed to this white paper that was later approved for implementation into a 10-year LSST simulation that you will see later on. So the key aspect of our first proposal of a potential strategy was to use LSST as a discovery machine. So what we have in mind is fundamentally to make the most of every instrument. So LSST has big field of view, can go deep. Okay, let's use it to tile the region of the GW of the gravitational wave source. But as soon as we are reasonably confident that we have a counterpart, then let's pass it on to some other instrument that has a smaller field of view, because in that case, the large field of view LSST would be just wasted. That's what we mean, LSST as the discovery machine, not as a follow-up machine for this particular science case. So this is what I call the old plan that we put out in 2018. We had one big overarching goal, which was to demonstrate that you can do fantastic science with what I consider a modest investment of time. As you can see, we came up with two potential strategies, one preferred, one let's call it minimal. And we demonstrated that with 1% of LSST time and maybe up to 2% of LSST time, we could actually do a lot of that. We could actually cover a lot of these counterparts, potential counterparts, and with a lot of color information. Again, color information means you can extract the physics of your merger. So this was the goal, and we also did not want to forget about our black hole mergers, and the reason being that for most of the follow-up surveys that are around, black holes are not up in their lists and in terms of priorities, but we think that one of the great potentials for LSST would be, given the depth, it would be to actually put a final answer to, is there a counterpart for a black hole merger or not? So venturing a little bit where maybe other surveys would not dare to venture. So what is the big message here is that with 2% of time, maybe half of it, we can actually do what I consider truly revolutionary science that cannot be achieved otherwise. I also want to emphasize that. So that led us to do a follow-up study that was based on the white paper in 2018. So we gathered together back again in the fall 2021 and stimulated by the Transient Variable Star leadership. And thanks to the great leadership of Igor Andreoni, we were able to basically formalize our 2018 plan and revise it somewhat. And again, I want to emphasize, just have a look at all the people here that signed and helped out with this paper. And I'm sure that a lot of these people are actually sitting in that room that I can see. So, we started thinking about what is the future of LSST, so in a realistic way. So we started thinking about 04 and 05. And just to remind ourselves about the current plan for LIGO Virgo Kagra, I put that cartoon on the lower right corner of your screen. And of course, the upcoming run is 04 that is supposed to happen around March in March 2023. The current duration is around 1 year. And I believe the next update from LIGO Virgo Kagra about their timeline is supposed to be on November 15th or around that. So I also put here a table that is taken from our 2021 paper, 2022 actually was published 2022 paper, where we quantified the number of gravitational wave detections with some constraint on the localization. So what we have in mind is a situation where we do not go after, if we will be granted to have TOs on LSST, we would not go after the random gravitational wave source, but we would select based on how well localized these sources are. And of course, we are in a situation where we can actually start to being a little bit picky and actually prioritize our follow-up on the better localized sources, so that the LSST can actually cover the vast majority of the area and can do that very, very, very fast. So I put there the expected numbers during 04, and I also put there 05 for a reason that will become very clear right now. So here I'm taking the same cartoon of the LIGO Virgo Kagra timeline, and then I borrowed some plots from a document that I think Raffaella linked in the Slack yesterday, I believe. It's a Rubin Observatory plan for an early science program. That's where I took this other images from. But what is the point that I want to try and make? That if you look at the current plan for LIGO, Virgo, and Kagra, there is a big gap between 04 and 05. And as of now, 04 is expected to end 1 year after, so March 2024, let's say end of March 2024. And then there is a big gap that extends to basically 2026. And then if you look at the LSST timeline right now, so it might be not as exciting, because it seems that we might be basically missing 04 with ComCom on Sky data, maybe. And so this is just to drive home the point that the big gap that is currently existing between 04 and 05 is presenting some challenges, not only for LSST plans to follow up these sources that seems almost to be entirely delayed until 05 with the big camera, but also for many other EM facilities. So if you have any power to talk to LIGO Virgo Kagra leadership, and if you have any power to make them extend the duration of 04, please join us making that argument. So what did we do? Well, we redid our calculations for what LSST should be observing for the case of our kilonovae from neutron star mergers. This is the counterpart that right now we understand the best. And we placed that kilonova, in this case, at 4 different distances, all the way to 300 megaparsecs, anticipating the improved sensitivities, especially during 05. And again, here the point is the same that as before. What we find is that we actually need to go deep, just like before. We also started playing around with okay, let's forget about the blue component and let's see how a red-only kilonova would look like. And the scientific reason to do so is that of the kilonova, the only part that is guaranteed is the red part. The blue part of the kilonova is not guaranteed to be there for every merger. So if we want to base our predictions in a safe way, we should base it on a red kilonova only. And as you can see, things of course become even more difficult because we don't have the help of the in brightness of the blue component. So yes, we really need LSST to help us out and try to find these counterparts. So what we started thinking about for this 2022 incarnation of a possible strategy is again to give priority to things that are well localized. And here we picked those 20 degrees squared that can be covered with a few LSST pointings. And I want to emphasize that the overarching goal for this document is again to bring home the point that we don't need an extreme amount of time. We can start with little amount of time. but a lot of science can be done with a fraction of a percent, 1% of the LSST time. Also, here is the summary. Please don't go through all the details, but what it means is that if you look at the amount of time during 1 year that we would need in our minimal strategy to cover neutron star mergers with multiple colors, is of the order of 22 hours during 1 year. And if we go down with our preferred strategy, we would need 30 hours in 1 year. So that's what we are talking about for counterparts that we know exist, and we have the best knowledge. Also, I do not want you to become too much attached to the different colors, different bands.
You have 5 minutes, okay?
Yes, thank you. I don't want to get too attached to the particular strategy that we put down there. What the main take-home point is that we want multiple colors. That's why our strategy has multiple filters. Why? Because that's the only way to constrain the physics. We need to get on target fast, because otherwise miss some components. And we need to cover as much of the area as possible and do it again until we identify the counterpart. So these are the key needs of any strategy that has any potential for success for neutron star mergers. I've heard about talking about smart strategies and not smart strategies. I really dislike this way of talking about strategies. For me, smart is whatever enables the best possible science. Given all the constraints. It might be that the smartest thing you can do at the beginning, given our complete ignorance about how some of these counterparts look like, the smartest thing you can do is just to go down to with every possible filter until you have a better understanding of what you're looking for. That's what I consider smart, is an observational approach that can actually answer to some fundamental questions and guide theory. So we did the same for neutron star black hole mergers. Let's just remind ourselves that this is a territory where we don't know what we are looking for. This is a territory where we can have all or nothing. And so again, there is extra motivation to be as agnostic as possible in our strategy, to be able to find what we do not expect. And we are talking about a little bit more time. Why? Because these neutron star black hole mergers, on average, they tend to happen farther away. Well, okay, we tend to detect them farther away in the gravitational wave part of the spectrum. So that leads to a little bit more of an investment of time. And let's not forget about our black hole mergers, and also our unidentified gravitational wave sources. And that's where we also budgeted in some time for to go after what I define more of something that looks more like a fishing expedition. Let's put everything together. You can see that our minimal strategy that we presented in the document asks for 1.4% of the LSST time. The preferred strategy is slightly below 2% of time. And again, what is smart and what is not, it depends on how much science is enabled, in my personal opinion. So here I stole a slide from Lynn Jones, actually, at the project and community workshop, where she ran some metrics to understand how disruptive we would be with our TOOs. And the take-home point is that we are not as disruptive. And a lot of the metrics for other science remain mostly unchanged. So to my knowledge, and people in the audience there should correct me, to the best of my knowledge, there has been no TO strategy that has been selected yet. So this is just a message to say that in our subgroup, we are getting reorganized to actually work and try to answer to many questions that you can see listed there as subgroup projects. So as I said, there are 235 plus minus a few, if I miscounted, scientists involved. We have very wide geographical representation. We have very wide dynamical representation in the state of the careers of people involved. We are heavily dominated by young people, but we have a fair representation. We also managed to get a lot of theorists involved with us to help us guide our reasoning. So this is just a way to say that these 235 scientists, that might become more if you are interested and want to join our subgroup, are representative of the community that is interested in this type of science. And I believe that is all I wanted to say. I just want to have one last slide of advertisement. This is not the only thing you can do with TOOs, and please attend Ham Smith's talk later today in your afternoon about how to use very deep Rubin TOs for lensed kilonova case. So the same case, same scientific case, but a different way to do it. And that's it. That's all I wanted to say. And happy to take questions. Thank you.
Thank you. Thank you, Raffaella. Can you hear me? Yeah.
Yes.
Thank you, Raffaella, for being perfectly on time and also for joining us so late in the night. So, there is a question by Giuseppe.
Thank you very much for this very broad talk and a lot of content. I have just a curiosity. Probably you mentioned, but I missed it. What is the difference of the TO that you would like to run on LSST when compared with the others that are already running on Subaru, DEC, KEC, or VLT? If you also take into account the fact that these facilities also have a spectroscopic instrumentation that is in place, so so have some advantage. So I was wondering what is the difference?
Yeah, so LSST, so one of the advantages is that, so in the southern skies, the LSST field of view and depth is unmatched. So you can cover the sky much faster at a depth that is scientifically interesting and meaningful. So that's a huge advantage of LSST. If you talk a Subaru, yeah, the hypersupreme can go also very deep. So if you talk about the northern skies, then hypersupreme would be the first competitor. I don't think it has the same field of view as LSST though.
Ciao, Raf. This is Bob Blum, Rubin Observatory. Hi, how are you doing? It's
pretty good.
Beautiful talk. Thank you. So I'm trying to wrap my head around actually how we would find the right thing in the images when we do all this. So can you help me understand that a little bit? So in steady state, and we're going to have to talk at some point about, you know, what happens in the next few years, because we won't be in steady state and we won't have everything running perfectly, but we'll cover a big chunk of sky for you, and we'll do a number of filters, and then you know, you could imagine there's an alert stream that's giving you every 5 sigma detection in that set of images over some short period of time. That's thousands and thousands of things. How do you narrow it down? And in your best case, how many things at the end of that short period of time are you then taking to some set of follow-up telescopes?
Yeah, that's a great question. And of course, okay. So templates, of course, you know better than me. Once you will have templates, that will help a ton. If you don't have templates, suppose that area of the sky, we could not cover it. Maybe if we are at the very beginning. In that case, the idea would be to use your first image as your template, and you do different imaging compared to that one. Or
we have a good template. How
let's assume, yeah,
how
so color,
narrow down the
right so by experience, colors and fast evolution, so the red colors and the very fast evolution of kilonovae, they are very unusual, and right now the transient that can really confuse us sometimes are reddened type 2b supernovae that are on the cooling envelope phase. So you can narrow it down pretty well, as long as we are talking about a neutron star counterpart. If we go into the world where we think we have a better handle of what we're looking for, if you go into the world of a neutron star black hole, then my answer would be different, because in that case, we would not know how a counterpart might look like.
Okay, thanks. So I mean, I think it's just something we're gonna have to learn as we go and understand what.
I could not agree more with that statement, and I would be a strong advocate for not going down with one strategy and that's it, but keep reevaluating how we are doing, and keep reevaluating how we are doing based on our findings and basically what you were saying. Were you able to find a counterpart or not?
Great. And one more brief comment. My colleague Steve Ritz reminds me that we only have the ability to do 5 filters in one night.
That's true. That's true. I know. We always have that plot with
Okay.
6. I'm so sorry. Yes.
It's okay. Great. Thank you.
Thank you.
Other question? Yeah. Come back.
As a solar system person, I care about observing time because my science doesn't get done if you're observing your field. And so I wanted to try to understand, why do you need all the filters going, right? If you know there's transients, right? Because you've gotten some filters.
Mhm.
How is that prohibitive to then go query Gemini, VLT, Subaru, to then go after them to get that? Because now you've narrowed it down, right? And so I'm wondering, why is it that I'm just trying to understand, why do you need every filter? Why do you need this, the time you're asking for? If the idea is, once you know there's a transient, you've got a good idea that you can then start farming out to all other small facilities. So can you explain a little bit more about why the color information is going to help you out, or what are the numbers expected that in terms of your false positives, you can't go trigger Keck and Gemini and BLT and be on those 4 transients to identify them out
Yeah.
of
Totally. Yeah. So the colors helps you understanding what is a plausible counterpart and what is not. Without color, it's really difficult game. I would never be able to pick a few of them. And in fact, I mean, when we tried before and after 1708-17, we would always get confused with typically type 2p supernovae, type 2b supernovae. So that's a main issue. So what you're saying of, as soon as you are reasonably sure that you have the counterpart, just pass it on to any other telescope. I could not agree more with you. I could not agree more. But until that point, and especially if we go down with the idea that we don't repoint everything, but are going to repoint only things that are very well localized. Let's go 20 degrees squared. So it's like few LSST pointings. I am a huge advocate for saying do it, and do it with all the filters so that you have the best constraints, and then you learn. And then you learn based on that, and you reevaluate. Is that worth to go down with all the filters or not? That's how I am a strong advocate for an agnostic observational strategy at the beginning.
Thank you, Raffaella. If there are no other questions, we monitor also on Slack. We don't have other comments here. Thank you again for joining us so late.
Thank you.
Yeah, and I would like to thank all the speakers of this session. We can go for the coffee break now. Okay.
Very quickly, the next session is our diversity, equity, and inclusion session. There will be some interactivity. And so you may want to spread out through the 3 rooms that are available. The speaker is remote, so you won't miss anything if you're not in this room, and you might gain some connectivity on the devices that are offering the internet to you.